Now we're going to look at writing and drawing some electron configurations. This is going to tie our lesson together with what we learned earlier. So here's a periodic table, and I have written on here the S, P, D, and F letters that we learned about last time, and you can see there are a whole bunch of other letters in here. And then what this periodic table represents is it represents how things fill up. So I like this picture here. It says that when you're starting to fill an atom up, you start with the first shell, and of course if it's hydrogen, you can put one electron in there, and then the next electron goes in that shell right there, and then that one is full. So then you go to the 2s one, which is, if you're just going along the periodic table, that one's full, and then you fill up the 2s. And then you go along the periodic table and you come to what's next. Well, it's the 2p is next, and that's what this diagram here is showing us here. So it's showing that once the 2s is full, you go to the next line, which is the 2p. And then once the 2p is full, the 3s goes next. And you can see that that is in fact next. And if you jump this middle portion here, then the 3p fills up next. And of course, that's what we've done. We've jumped up to this line here. So now we're filling the 3p followed by the 4s. And then we hit the d's. All right, now, and this is how electrons are filling. So if you want to figure out what the electron configuration of something is, you just need to look to the periodic table and look at these different letters that are put on here and numbers and follow that. So that's what our lesson's about. So let's take a look at that. Okay, so the Aufbau principle, an atom is built by the addition of electrons. Electrons begin filling in the lowest energy level before moving on to the higher ones. So the s orbital gets filled before the p orbital can begin to fill. Energy levels or orbital diagrams show the location and spin of all electrons in an atom. So here's an example of one. And you can notice that we have our s, and it's about energy too. So it's saying that our lowest energy is with the s, 1s, and then 2s, and then 2p is slightly higher, and then 3s is next, and 4s, and then it jumps to sorry, that's a 3p, then a 4s. And of course, these numbers are again coming from the periodic table. If you just trace your finger along and it's labeled, you're going to come to, say, 4s before you come to the 3d. Just look at the periodic table. So let's draw orbital diagrams for the first 8 elements. So there is that periodic table I've been talking about. And we're going to do the first one, hydrogen. So you start here, you say, oh, okay, I was partially able to fill up the 1s. I'm going to put one arrow pointing up, and that one arrow pointing up represents one electron. Hydrogen's number 1. It's got 1 electron. So what have we discovered here? We've discovered that hydrogen has an electron configuration of 1s, and they write it to the power here, so it's to the power of 1, and that 1 is representing that, and that 1 is representing that one right there. Okay? So that's hydrogen. Well, let's go to the next element. The next one is helium. Let's see, so we'll start at the beginning of the periodic table, and we're able to cover up the 1s. So how this looks now is we put our first electron pointing up and our second one pointing down. This up and down is in fact representing the spin that we talked about last lesson. So we could say that maybe that first one is representing a half spin in positive, and this is representing a negative half spin in the other direction. And what we've discovered is that helium has an electron configuration of 1s to the power of 2. So 1s2. Again, that 2 is coming from those 2 electrons. Next one, lithium. All right, so we'll draw on our periodic table. So we start at the beginning. We're able to fill the 1s. And there's lithium number 3. We got to stop right there. And so it gets us into the 2s orbital, like that. And our electron configuration will be that. We have 3 electrons, and we have 3 numbers there if you think about it. Let's do beryllium. You start at the beginning. You're able to fill the 1s. Now we're actually able to fill the 2s. And there is our configuration. And now we go to boron. And we go to drawing again. So we fill the 1s. We fill the 2s, and we jump all the way across here, and there's boron right there, and that gets us into the 2p. And that one points up. Boron has an electron configuration of the following. Now, a little something will happen when we get to the next element here. Carbon. So we'll draw it first. Here goes carbon. We fill the 1s like that. We fill the 2s, and then we stop here because there's carbon. And When we add the next one, we don't pair them up, we actually put it like this. Now, this is actually can explain some of the charges on the periodic table that you've seen for carbon. Carbon has sort of multiple charges. It can be plus or minus 4, or it can be plus 2. Well, let's talk about that plus 2. It actually comes from the fact that those 2 electrons can be lost, and we have an overall charge of plus 2. So that's one way. Where does this plus 4 come from? Well, the plus 4 says we've lost 4 electrons. Well, look at that. Those are the 4 electrons that we'll lose to have a charge of plus 4. And then the opposite case here is it can have a charge of minus 4. And I'll do that in another color here. What could happen is we could add in 4 electrons, and look at, we would fill up its s orbital. And that's why it would have a charge of minus 4. Nice, eh? And there's your electron configuration. So these things can help us explain charges on the periodic table as well as the group number. Nitrogen. I'm just going to go ahead and fill this one in, and we have them all pointing up. So we're halfway through the p orbital. And again, you can think about the charges that nitrogen forms, you know, plus or minus 5, plus 3, or sorry, minus 3, I don't know what they are, look them up. And oxygen, when we get to this one, has one that goes down. So we have our very first pair there in the p orbitals. Now I've changed it here. We jumped way ahead to gold. Gold is number 79. It is approximately, I'm just trying to eyeball it, somewhere there-ish, we'll say. So we have a whole bunch of orbitals to go through. Now let's keep in mind that this f orbital should actually be like right there. Okay, it's just been cut out of the periodic table. So here is our final finished diagram, and it's got a crazy electron configuration. So let's see, we can fill the 1s, you fill the 2s, the 2p, the 3s, the 3p, the 4s, the 3d. It goes on and on and on. We're actually able to fill the 4f. And again, if you look at the atomic numbers on that area there, it starts at cerium at 58 and goes all the way up to lutetium at 71, and we know gold's 79, so that's where we kind of jump back here, and then that gets us to 79. Now, this is one of the things that you're going to be doing later, is writing these out, and there is a short form, happily, is you actually jump back to the most stable and nearest noble gas. Really, it's just the nearest noble gas in this case, which would be xenon. So you put xenon in brackets, and that stands for all the stuff right there. So all that stuff I'm circling in red is represented by that XE right there. And so then you've just got a couple of little things left to write here to give you gold. And I guess, sorry, that S2 would have been out there just because of the energy. My bad. I colored over the S. That was incorrect. I'll live with it. So I like this analogy of electrons filling up. It's like they're saying there's a stage here and you're on the stage, and then the rows are going to represent the orbitals where we're going to put electrons. So in section 1, we're able to fit a couple of people, and that represents our S. So S orbitals can hold 2 electrons. Then when we look at our next section here, again, we've got another S orbital, and we've got a couple of electrons, and then we've got a P orbital. There's our row P, and it can fit up to 6 electrons. We talked a bit about L, and we said in this case that L could be +1, it could be 0, or it could be -1, and we can kind of randomly assign these. We can say that's 1, that's 0, and that's -1. And finally, when we get up to the D's here, again, our S's can hold 2, our P's can hold 6, that's 8 total, and then our D block can hold 10 if you count these. 10, and so really we can hold 18 by the time we fill up that D orbital. So what I want to do here is I want to show what the shapes of these look like. Let's tie it back to last lesson. So we've got hydrogen here, and it's got 1 electron, so it's a 1s, so it's a circular, and let's say that's our electron right there. Now we got helium. It has 2 electrons. I'm going to put the 2 electrons right there, and they're good to go. And now lithium's a little more complicated. We've got 3 electrons, we put 2 there, and then we're actually up, so that fills the 1s. And now we need to fill the 2s. Well, what happens is the 2s is a bigger circular orbit. We know s orbitals are round. So we got another electron there. And again, this electron can go any which way. Heisenberg says we don't know exactly where it is, we just know it's probably in there somewhere. Beryllium has 4, so I can put 2 in that first shell, and then I can get 2 more there, and that is good. Now watch what happens when we get up, because look at the next one. We're going to have the P's here. We know P's are different shapes. So here is our boron. It ventures into the P. So there's our 1s, and we can have a couple of electrons. There's our 2s, 2 more electrons. Now what happens is we get all these p orbitals here, and that 1 extra electron right there can go in any one of these. It's probably going to go in the X one first, and I already kind of went past that, but we'll just go with that. That's good. So when you look at carbon here, it's got 6. So when we get out to here, it's going to have 2 flying around, and nitrogen has 3. So all those sort of fill up, you know, maybe there's your one for nitrogen, and then there's the second and third ones. So electrons, again, are found in those shapes somewhere. So now am I smart enough to know why science has been lying about Orbital diagrams to me for years? Because in the past, what we told you is that the first shell can hold up to 2 electrons, and then it's full, and then every other shell after that can hold up to 8 electrons. And this is right and correct for the first 20, but what happens when we hit the 21st element? So why can we only draw them for the first 20 back when you were in younger grades? Well, let's look at calcium, which is number 20 here. So I've written it out, and you can just please ignore these yellow numbers here. They don't mean anything. So there's our electron configuration for calcium. And here's how it fills. So it's telling us that we've got the S1 filled, we've got the S2 filled, we've got the S3 filled, the 2p filled, what else have I got here? We've got the 3p filled, and we've got the 4s filled. Okay, so these are all filled. And if we just draw, I'm going to draw over this here. It's saying that that one's full, then we fill that, then we fill that, and then we fill that. And look at what comes next, the 3D. Now again, we've been talking about putting electrons into the 4th electron shell. But what this is telling us is that the next electron that goes in actually goes back into our 3rd orbital. If you watch here, there's our 4th one, but it actually is going to go into that one right there. So let's skip ahead to scanmium. So there's our electron configuration of calcium, and what we need to do is we need to add that 1 extra electron in, and what we're going to do is it is going to go into the 3D, right? There it is. And so what I need to do is I need to put another one in the 3rd valence shell there. Again, what you might have thought was you might have thought it went in the 4th one, but that's not exactly correct. And then there's our short form. So what we are now ready to hear is that the different orbitals can hold a different number of electrons. And I did already kind of allude to this back on our slide where we were showing how the electrons filled the seating for a play. So what we've learned is that the S shape can hold up to 2 electrons. And if you look on the blue boxes there on my picture, they are all sort of 2 in a row, right? Even if you look at hydrogen and helium. And then you look at the P ones, the green ones, there are 6 boxes in a row there, all piled on top of each other. And the D, there should be 10 yellow ones there. And then the F ones, there should be 10 gold ones. Now this sort of harkens back to this picture which we looked at last time in our last lesson, and I think we're probably ready to figure out what the heck it's talking about now. So when we're talking about a value, we've got 1 shell. What that says is that we've got an s orbital, and it has no spin because circles can't spin, right? No matter which way you look at it, it's still a circle. And that we have 1 orbital, and within that 1 orbital we can fit 2 electrons, right? So it's like saying 1 times 2 gives us 2. So that's how many electrons we can fit in that orbital. Now when we go up to the 2, we've got 2 orbitals going on. We've got a 2s and a 2p. When we're looking at the circular one, we've got 1 times 2 electrons, so there are 2 there. And now we've got, remember these stand for the F shapes. There are 3 different F shapes. There are 3 different, sorry, these are P shapes. So we've got 3 different P shapes, and that's why we have 3 different orbitals. And remember that we can fit 2 electrons in each orbital. So we should be able to fit 6 there. And this one was 2. And what's 2 plus 6? That equals 8. And then when we get down to the 3s, we've got 3s. So we can fit 2 electrons in that one. We've got the 3p with its 3 different orientations. We can fit 6 in there. And then the 3d can fit up to 10. And you add those numbers up, and they equal 18. And then you can do the same thing here. And these are all doubled, and that adds up to 32. All those numbers added up. And then there's kind of a general equation to do it if you sort of forget. So there you go. Can you explain the charges of the transition metals or the d block metals now? Can it be explained why some of these metals have more than one positive stable cation? When you learned about ionic charges in previous courses, group 1s were +1s, group 2 were +2. But then when you got to the middle block, suddenly it was all crazy. Well, let's take a look at some of the ions that are formed here. In fact, I want to look at the lead here. Lead is number 82, and here's its electron configuration. Now, what happens when we get to the +2 ion? Well, if you compare, what's actually happened here is we've actually lost the 2 that are in the s orbital, or sorry, in the p orbital. They're no longer there. You've lost 2 electrons. You have a charge of +2. When we look at the one that's +4 here, what's happened is we've lost everything in the s. Both of these are gone, and we end up with this configuration, and that's why we have a charge of +4. Let's take a look at another example here too. What about iron? Because that's a popular one. It's +2 and +3. And so what I went and found here was I went and found iron's neutral electron configuration, and you can double check that. Now here's what happens when we have a +2. If you compare the two pictures, we have lost, that electron has vanished, and that electron has vanished, and now we have if you've lost 2 electrons, you have a total charge of +2. And if you look, we have some nice symmetry here. We've got one, in fact, we've got one kind of in everything here, don't we? So that seems to be a more stable configuration than, I'm just going to jump back to the original picture here, if, say, this one lost, that one there, and that one there. We would have 1 standing up, 2 standing up, 3 standing up, 4 standing up, and then these paired up. So apparently this is just a more stable configuration. And there it is, there's the proof. We've got something in the 1s. And what about the +3? Well, what happens with the +3 here is we actually empty these ones here are gone, and we empty one of these. And so that's how we come up with that orientation. And we have emptied the 4s orbital.